Sort of the end of what I'd planned to cover this week, but there was very little discussion on the first day, so we basically got a full lecture ahead of time. But one thing I'll mention is so I changed the material in various places, but this week we've largely focused the first month of my graduate class. So we did like a month worth of material in a week, so as you noticed, it was very fast. But the course is 3.5 months long. So if you want to see the other, almost 3/4 of the course, you can Google CPSC 540. Now, the rest is not really optimization focused. It's focused on different sort of modeling issues, gets into more counting problems and solving integrals and Bayesian methods, how to model interactions between variables, deep learning, things like that. So these are machine learning courses. And then there's also, if you're more interested in the machine learning side, the undergrad course is called 340, and all the notes and assignments and things are all online, so you can just look all that stuff up. So if you want to learn more about applications, then look at 340, and there's lots of pictures and lots of lists of applications and different sort of practical issues, which I've sort of skipped over here. So if you want to learn more, just Google those things. So for this last lecture, where we're not going to talk about the course material at all, I picked two other issues which I think are very important in the future. So one thing is parallel and distributed optimization, which I'll motivate shortly, but I'm sure many of you already know the motivation for why this is very important. And then I'll talk about non-convex, and I'll briefly stop to motivate why non-convex problems are becoming an incredibly hot topic. Okay. So to motivate parallel and distributed, we just need to look at these two recent trends. There's a bunch of other reasons, but we just need to look at these two. So we aren't making large gains in serial computational speed. So when I was young, we maybe bought a computer every like X number of years, and it would be like X times faster, or maybe X1 and Y, where Y is like much bigger than the number of years. So it used to be that you had a 1 megahertz computer, and then a few years later, you bought like a 100 megahertz computer. It's 100 times faster. That's not happening anymore. The computer I had 15 years ago has the same clock speed as the computer I have on my desktop now. It's more clever. It's 64-bit. It's got pipelines, so it's faster in practice. But in terms of just like how quickly can you turn the clock, it's the same. Another issue is that data sets are no longer fitting on a single machine. We have collections like the internet, or trying to map everything in the sky, things like that, and they just can't fit on your hard drive anymore. So your data is going to be spread across multiple machines in the future. So the result of just these two trends is that we need to think about parallel and distributed computation. If you want to handle bigger data sets, if you want to solve harder problems, this is a necessary evil. You need to learn about these things. You could go on talking about the motivation for an hour, but I think it's not hard to convince you that you just need to think about these things going forward. You're going to need to think about doing things across multiple computers, across multiple cores, across maybe on a GPU, whatever, or a computing cluster, and you're going to need to think about where my data is located. How is my data spread around a network or something like that? So some issues, so you have the usual issues of convergence rates and algorithms and non-differentiability and strong convexity and so on. But some other issues that show up are, one is synchronization, is that you often don't want to wait for the slowest machine. And one is communication, which is that you can't transfer all the information around. You can't fit everything on a single machine. And communication is expensive when you're in these distributed settings. So before I go on, I'll give the disclaimer that some of you know more about this topic than I do. So forgive me if I say anything ignorant, or maybe just bring up some discussion if there's things that we should be adding to this. But I'm just going to make a few points of some of the works based on a survey that some of my colleagues made me write a few years ago. Okay, so the first thing I want to say is a lot of machine learning problems are what's called embarrassingly parallel. And embarrassingly parallel is really a technical term. It's a fun technical term, but it means I can basically split my task across m machines do some independent operation on every machine, and then have some simple way to combine them. So embarrassingly parallel means that there's some way to just decompose my problem into something that each machine can work on, and then I have some simple way to put them together. And in this case, if I have m machines, I can just solve my problem m times faster. And unfortunately, there's no superlinear speedups. So this is, in fact, the best you can ever do by parallelization. So there's the answer. If you can do that, that's what you want to do. And in machine learning, there often is embarrassingly parallel solutions. It's not nice, it's not fun to write papers about this, and you're not going to get published by doing this, but in practice, you should always think about this solution first. So for example, if your big issue is you want to compute the gradient of n examples, and n is very large, well, I'll just write this gradient as the sum of m different sets of terms. Machine 1 computes this part of the sum, machine 2 computes this part of the sum, machine 3 computes this part of the sum, and then maybe they send them all to one central machine that puts them together, and now I can do my gradient step on a huge data set. There might be communication costs that make that not the ideal thing, or the bottleneck might be elsewhere. But if the bottleneck really is n, and this communication cost isn't too bad, you should just do this, and then call it a day. So that lets you do the optimal linear speedup, and that's always what you should consider first. And I think that sometimes when you write papers about parallel and distributed, this warning should always be included. In that you should mention that you should always say that the embarrassingly parallel solution is not possible in this setting, so we're looking at something more clever. Okay, so the asynchronous computation. One issue is, do we have to wait for the last computer to finish? So let's say I do the embarrassingly parallel solution, but I have one computer that's just much slower. Or I couldn't divide my data set up evenly for some reason, so one computer has less data than the others, or more data, or something like that. So should I have to wait for all the computers to do their operation, which means I have to wait for the slowest computer before I do anything? And that's where asynchronous computation comes in. In a lot of settings, it makes sense to update asynchronously to do something different. So one of the examples that's been looked at is stochastic gradient on a shared memory computer. So what this means is that you have, let's say, 16 processors, and they all share the same RAM. And so what you can think of doing is having each one go grab an example, do the stochastic gradient update, and update the memory update your XK in RAM. And the 16 are kind of just doing this simultaneously, and none of them is waiting for the other. It's especially important if you have sparse data, where some vectors might be much more sparse than others. So some of these might take a long time, some of them may take a short time. You don't want to wait for things to finish. To make that work is a very simple thing. You just need to decrease the step size, and roughly in proportion to how asynchronous you are. And this is, yes, please correct me.
Yeah, just comment about that gradient. That direction might be a direction of ascent. Right? You are using the point xk, you are moving to a different direction to find an xk minus n.
Yeah, so that was also true just if I'm doing stochastic gradient. So even with stochastic gradient, that might be true. Now it's worse, though, because now the expectation of this step may not even be a descent direction. So the trick is you really need to make the step size alpha much smaller. And if it's smaller, you can show that this doesn't hurt you too much. So this was, I think, it's called Hog Wild. And it's definitely my favorite in the bad acronym club. And the exclamation mark is part of the name. So so New, I think, was the student, but it was Stephen Wright and Ben Recht, who are very strong researchers. But this name is ridiculous. Not great at naming, maybe. The exclamation mark is really funny. Like, but the punctuation is part of it. No, it's not a question mark. It's an exclamation mark. So roughly they show that if you have a delay of m, so m is like the oldest iteration that you could be working on. So all of your cores are doing a stochastic gradient step simultaneously, but some of them might take longer than others. And so we're saying m is the most, is the oldest one you can have. So the longest delay you can have on one core compared to the other ones, which are using new versions of the parameter vector. And they show that this is okay. They released a code, and actually, I've heard that, I haven't used it myself, but I've heard that it's very fast, that it works quite well. Okay, but I know some of you are actually working on asynchronous algorithms. Do people want to add anything before I switch to the communication issue? Yeah, of course. So I think that's again a usual stochastic gradient problem. Here's another issue is, okay, I say you just need to decrease the step size. Actually, if you don't know the asynchrony, and this is also going to depend on things like Lipschitz constant, you actually don't know how much you need to decrease it. And this is related to the issue of not knowing the function value, is if you knew the function value, you could just test if your step size is small enough, but you don't know the function value, so you don't know how much to decrease it. So even though theoretically it works, in practice there's kind of a tuning problem that needs to be solved. Yeah. So actually, a student in my class who publishes in places like supercomputing, whose research area is specifically trying to make things as fast as possible, he actually said that asynchronous slows you down. Because he says there's some like special things in the hardware that lets you do things synchronously faster than you can do them asynchronously. So in terms of pure runtime, he actually found that asynchronous was slowing him down. And so he removed it. And he wrote a paper with the people at Intel about this and published it at Supercomputing of sort of, I guess, synchronous parallel stochastic gradient and sag. Okay, so another issue we need to think about in this setting is reducing communication. So in that embarrassingly parallel thing, I'm assuming you can actually pass the parameter vector to every computer, and I'm assuming you can pass the gradients back to some central computer. But that's expensive. If you have a huge number of variables, these are big things to pass around the network. And communication tends to be much more expensive than moving things around in RAM or in caches or things like that. So we need to reduce communication. One solution by Peter Richterich and his group is parallel coordinate descent. So this is kind of like the Jacobi style coordinate descent instead of the Gauss-Seidel, where I'm going to pick a bunch of different coordinates, and each computer is going to do coordinate descent on one coordinate. And so if I do this, I can actually reduce the amount of communication that happens to go around the network, because I'm only changing one parameter at a time. For convergence, the main trick is, again, you just need to reduce the step size. You can't use the usual step sizes, because if you move simultaneously along two coordinates to their full length, you can actually increase the objective function, which shouldn't happen with coordinate descent. But if you decrease the step size, this can work. You can also analyze the speed up of you can get, and it depends on things like the density of the graph. And Peter and his colleagues have another condition they call essentially separable optimization or something like that, which lets you try and theoretically characterize how much of a speed up you can gain by parallelization of coordinate descent. Okay, another thing you can think of to do reduce communication, and also when you have distributed data, which I thought was really neat, is called decentralized gradient. So here you actually have to distribute the data across machines, and we don't want to have a centralized vector x. So in the embarrassingly parallel solution, I imagine there was one like supercomputer that's keeping track of like the gold standard x, and he's sending that x to everybody, and then everybody sends the gradient to him. But this is very inefficient communication-wise. There's a lot of data being passed around that you may not want to do. Or rather there's a bottleneck in that if you have to wait for that guy's pipe to open to actually send information. So you're sort of creating a communication bottleneck. So one solution to that is something called the decentralized gradient method. So in this case, each processor has its own part of the data set. We've split the data set across processors. We're not going to worry about how they got there. We're just going to assume that they're there. And each processor also has its own parameter vector xc. So xc for processor C. And each processor is only going to communicate with a limited number of neighbors. So machines can't directly talk to every other machine. We're assuming you have some fast way to communicate with a limited number of other machines, but you're not sending things multiple hops across the network. We're going to have that be handled by the algorithm. So the decentralized algorithm looks like this. So let's ignore this part of it for now. We're going to take a gradient descent step just with respect to the data on my own machine. That's the basic step. But the difference is to take into account what is on other machines is instead of taking my parameter vector, I'm going to take the average of my neighbors in the graph. So we imagine two steps here. So in each step, everybody sends the x to their neighbors in the graph. Then each node averages the values of its neighbors, and then it takes a gradient descent step. And now you go back to the first step where you broadcast to all your neighbors. And they're going to take the average and take another gradient descent step. So gradient descent is roughly a special case when all the neighbors communicate with each other. This does not actually converge. It doesn't quite work, but there's a modification you can do to make it converge. And so if you have that modified update, you get this very elegant analysis showing that the convergence rate is going to decay based on how connected your graph is. And in particular, it depends on what's called spectral graph theory. So you have to look at the Laplacian graph, and then the spectrum of the Laplacian graph is going to tell you how much you lose with different ways of communicating between machines. There's also been, this wasn't for decentralized gradient, but in another context where you actually look at communication failures or machine failures. So what happens if sometimes the machine just fails? Like if you're talking about settings where you have thousands of machines, there's some possibility that one of the machines is just going to do the computation wrong, or it's going to be rebooted, or something else can go wrong. So some people have looked at how you can be robust to failures in the network, which is important when you start thinking about large systems. Okay, so that's all I really have to say about parallel and distributed, because I'm not an expert on this topic, but I think those are sort of three neat issues to think about, and they're going to be more and more important in the future. So maybe I'll open up the floor and ask if anyone else has any other comments on these issues. Yeah?
About the step sizes, right? I think you mentioned that is there some computational studies saying how robust or how good it is? You don't share all the step sizes between agents, you know?
So I think in this work, and probably in all three of these works, they don't really think about practical step size issues. These are all sort of theoretical papers and some implementation where they've tuned the step size. So there's a lot of work to do on how to implement these methods in practice. And I don't think there's elegant answers for these questions. Yeah?
You mentioned that the communication time can be a bottleneck.
Yeah.
But if the time you need to evaluate each function is high, is large, then you can neglect this communication time.
That's right. So if the time to evaluate the individual functions is very high, I can just do the centralized thing. So then I can just be embarrassingly parallel. So this is really for objective functions where I guess the communication cost and the computational cost are similar. Now there is a version of this algorithm where they use, I can't remember if it was either SAG or SVRG. So if you're thinking that I should be stochastic on the machine, somebody's already published that last year. I think there's also an asynchronous version of this algorithm too that exists, or if there isn't, someone's going to put it on archive in the next like 6 months, I would guess, because it's an obvious thing to do and it probably makes it work much better. Okay, any other final comments on parallel or distributed or questions or anything like that? My knowledge of this is mostly limited to papers I've read, and I did a graduate course on parallel and distributed computation, so where we proved that like you can't have superlinear convergence and things like that, and talked about embarrassingly parallel. But I made all my students take a similar class this year, or not all my students, but all the new students had to take this class because I was like, this is going to be so important. Another fun story is Andrew Ng, the person who's become extremely famous in machine learning and extremely rich, working for Baidu. He was visiting our lab maybe like 10 years ago, and we asked him what he thought would be really important in the future, and he's like, these GPUs. He's like, I think you should learn how to do computation on GPUs, and that was very insightful because if you want to solve huge problems, actually beyond these things, how to write your problem on a GPU is now important because you can actually make it go like 100 times faster. So you can get those sort of classic speed-ups from the 80s and 90s where your computer would get 100 times faster every year if you get a fancier GPU. So another neat thing is NVIDIA has this program where they will send you GPUs. They will send you fancy GPUs for free for research purposes. So I would highly recommend doing that. My students love them. Yeah, it's just overnight, with a few changes to your code, it's so much faster. So I guess I don't have any slides on GPUs, but use GPUs would be a general recommendation. learn how to do CUDA or something like that. Okay, so the last topic I want to talk about is non-convex problems. And here's another thing you should look up. And I'll put it in capital letters. So I have some slides, but I'm not gonna. You can get them from the course webpage. It's called, if I can spell, deep learning. A synonym for this is neural networks, which you may have heard of before. So neural networks are back. Yes. So what I've been talking about this week is called, in a derogatory way, shallow learning. So here the idea is, how do you pick your basis? Or at least in the supervised case, it's how do you pick your basis? So I sort of dodged this question. I didn't give a real answer to this question. I said it depends on every application. It requires some tuning. It requires some knowledge, things like that. In the supervised case, deep learning is all about learning the features. And you learn the features as a sequence of compositions of simple operations where you learn the parameters of the compositions. And you can start doing neat things like showing that you actually don't need to do maybe too many compositions to model very complicated functions. And so you learn how to do these compositions, you learn the features for your task, and you can actually solve very complicated problems. So the modern thing, the modern view of deep learning was actually a Canadian thing, or a Canadian initiative. This Canadian Institute for Advanced Research funded Jeff Hinton, Yoshua Bengio, and Jan LeCun, who have all, I guess Bengio is still in academia, but LeCun is now head of AI research at Facebook, and Jeff Hinton is running a group at Google, so they've been very successful. It was put together to sort of bring back these ideas that were popular in the 60s and were also popular in the 80s and sort of bring them into the future. And the first really big thing that made noise was in 2009 when they showed that for speech recognition, so you talk to your phone and it tries to figure out what words you do, these methods just work substantially better than all previous methods. And the ingredients there was really a big data set and an absolutely enormous model. But within 3 years, in 2012, basically every phone had switched to a deep learning method for speech recognition. And so all of your smartphones, if they have any sort of speech recognition, it's based on one of these models right now. That was part one. Part two was 2012, when they came along for computer vision. So I give you an image, and you want to tell me if that's a cat or a dog or a car or whatever. They actually are doing thousands of classes now. So this has traditionally been viewed as like an absolutely impossible task. It's something humans can do very easily. We have no idea how to make computers do it. They put deep learning and combined that with GPUs and a huge, huge data set, and they just destroyed the competition. So since about 2012, the error rates have gone from something like 38% down to this year was 3%. And this is a system that can distinguish between like a Siberian Husky and some other type of like white, very similar husky-looking dog. Like it's really impressive the things that they're doing. Like so they're arguing that this is basically at human level accuracy for this task of saying what is the main focus of this image. And so they're very impressive systems. Google and Microsoft and so on are investing a lot of money building these deep learning models. So I think there's a Coursera course on this too. So if you want to learn about it, you can do that online too. But for the future, this is probably going to be a very important topic that's going to be affecting our lives for a few years to come. That being said, things come and go in waves. So shallow learning may very well become very popular again. So it's always hard to predict what's going to happen in the future. Okay, now the reason I use that as motivation, these models are always non-convex. And they're not even a nice, very non-convex. They're a nasty non-convex problem. So I want to start talking about non-convex optimization, because in my field, this is where everything is going. And deep learning is also a little bit crazy in that if you write a paper on this topic, you can get like 5,000 citations in a year. Like it's hard to underestimate the academic impact that these works are having. Or you can get hired by Elon Musk to run your own AI initiative. That happened to one of my friends. Okay, he left Google. All right, so some classic perspectives on non-convex optimization. One is the local perspective. Is even though I have a non-convex problem, I'm just going to apply a method that has good properties for convex functions and hope for the best. So the classic way to do this is you have a first phase where you say you get near a minimizer, possibly a local minimizer, and then the second phase is, well, now that I'm near a minimizer, this looks like a convex function, so I'll just apply my analysis for convex functions. That's sort of that shows up in a lot of textbooks. But of course, you need to know how long the first phase takes, and you also need to think about what is the quality of the minimizer you get to. The second perspective is the global non-convex optimization perspective. Is I'm going to actually search for the global min in some general function class. So we can do things like grid search or genetic algorithms or any number of things, simulated annealing and so on. And as I mentioned on day 3, I think, the optimal rate is 1 over epsilon to the, I guess that should be d, not 1 over d. So the issue here is you can really only solve low-dimensional problems because you have this nasty dependence on d. So I'm going to go over some recent local, global, and hybrid results, but these are sort of the two classic perspectives. Unless people disagree with me. This is just based on my own literature review of the topic. I guess we've also got things like convex relaxations. Yeah, so you take some convex function and you try and make it as close to the non-convex function as possible. So that's another thing. Are there other perspectives, or? Because it almost seems like there should be something in between these two extreme cases, like saying we can only solve low-dimensional problems versus problems where we don't really know the quality of the solution. Yeah, that's a good point. So you could use duality to get some sort of certificate of how good the thing is. Yeah, that's a great point. Okay. So first, we're just going to be a little bit non-convex. So before we assumed we had strong convexity, and that was to get a linear rate. But actually, you can show linear convergence under a whole bunch of weaker assumptions. There's things like essential strong convexity, weak strong convexity, restricted secant inequality, I think that should be restricted strong convexity, quadratic growth property, optimal strong convexity, and error bounds. There's a lot of them, particularly in the last 5 years. And in fact, if you looked at the proof we did on day 2 or day 3, the only way we used strong convexity was actually to get this inequality. And if you actually look, there's a paper in 1963 by Polyak where he shows that this is all you need to get linear convergence. Another neat thing, which we showed just in the last few months, is that not only is Polyak's condition older than all the above, it's actually weaker than all of these conditions. So if you assume any of these conditions, actually except the quadratic growth property, but there's a other reason why you don't want to only assume that. But all of the other ones actually imply this inequality. So a lot of these newer conditions actually were not weaker. Some of them generalized to constrained scenarios, so I don't want to completely sweep them under the carpet. But if you're just thinking about unconstrained smooth problems, what I'm saying is you don't need to know what any of these are. So hopefully I just made your life easier for some of you. You can just skip straight to this one. I forget what they were, many of these you only need them to hold locally. So the reason I'm saying this is I'm going to use this to prove global rate, or you can use this to prove a global rate. Yeah. So I think any of the conditions you could say that they would only hold locally and get something, I believe. Yeah, that's true. So actually, if you want linear convergence, can you just have to be more than linear? Not sure. Don't know. I actually told my student to look at exactly that question. So maybe. Okay. I was hoping you could give her the answer, but okay. So one thing about is if we just assume this condition, it doesn't imply the solution is unique. You also have some problems, like if I do f of ax for f strongly convex and a being singular, this condition will still hold. It will depend on the smallest non-zero eigenvalue instead of just the smallest one. And this condition doesn't imply convexity. So there are non-convex functions where this is satisfied. They're not super interesting. They still roughly look like quadratic functions, but they can have non-convex parts. And this condition, this will also work for coordinate descent and proximal gradient and SVRG and all that sort of stuff. So if you assume this, you can prove all the rates we talked about, but for a more general class of functions. I'm just assuming it globally, but you can probably weaken it to just have it being holdable. Yes, that's right. So there may be more interesting functions where this only holds locally. And so actually, Julie, my student, had her proposal defense last week, and I asked her that question. I was like, how can we generalize this even further? And she unfortunately didn't give that answer, but I think there are more general classes where you can have this. But I'm not quite sure how you would characterize them. So if you have any thoughts, please email me. Okay, so just contrasting. So before. We had strong convexity, which means your functions roughly look like this. You have a unique optimum. They're convex. They grow faster than linear. And I'm not completely happy with this picture anymore. It's a little bit exaggerating how general it is. But you can now get linear convergence for functions that look kind of like this, where you have flat regions. They have non-convex parts. And they still have to grow faster than linear as you go away from the solution. So you can interpret that as either there are some classes of functions where we get linear convergence that we didn't see before, or rather that people forgot about since this Polyak paper, nobody really cites it. Or you can think of, if I'm doing a non-convex problem with 2 phases, the second phase where I get linear convergence is actually much bigger. You can once you get to something that looks like this, now you can get linear convergence, as opposed to before where you may have had to get very close to the solution. Okay, so another topic. If I'm talking about strongly convex smooth functions, I can prove that the iterates converge, the functions converge, and I can prove that the gradient norm also converges. The row here I think is slightly different. If I start talking about convex functions that are not strongly convex, I can still show that the functions converge, and I can still show that the gradient norm converges. And if you go to non-convex functions where your Lipschitz is continuous, you can actually still show that the gradient norm converges at a certain rate. So instead of just showing that you converge to a stationary point, also assuming it's bounded below, you can show that the gradient norm is converging at a certain rate. So this is a convergence rate in a much weaker sense. It's not saying anything about the quality of the solution, but it is saying sort of how fast gradient descent can get to something that looks like a stationary point. And recently there was a generalization of this for stochastic gradient, where Gnevy and Lan looked at some way to randomly pick an iteration k, and they showed that for that random iteration you had the 1 over t in expectation. So it's showing that stochastic gradient actually finds things that look like critical points fairly quickly too. So yeah, it's really not satisfying because there's no f, there's no distance to the solution, but it's saying something about how fast these methods converge. And this has been generalized to mirror descent type of things, and one of my students generalized it a bit further. Okay, so this type of rate could be good news or bad news. So one is that there's no dimension dependence, so there was no d in that rate, unlike with grid search, but you're not getting optimality. So you could hit a saddle point or some other non-minimizing critical point. There has been a lot of work on escaping from saddle points. So the classical approach to do this is use a trust region method, where you have the Hessian, and then if you have negative eigenvalues, well, your trust region problem can actually follow direction of negative curvature and get out of a saddle point, which is a little bit different than line search methods, which can have more trouble. There's been some recent work looking at modifying the eigenvalues in Newton's method with a line search style thing, or adding random noise to stochastic gradient, or even gradient methods. So there was a paper more recently by I think Ben Recht and Mike Jordan showing that actually gradient descent is not really going to converge to a saddle point unless you give it a ridiculous initialization. So that was kind of a neat result. And then in this cubic regularization paper, they looked at a second order method where you have a cubic term here, and they proved that once you get close enough to a saddle point, you actually move to something away from the saddle point that has a lower objective. So if you go to second order methods, you can escape saddle points. But there's been a few recent works sort of proving that that first order methods are also not going to converge to saddle points. One caveat of that is, of course they're going to. If I do x cubed, and I start here, and I do gradient descent with 1 over L, it's going to converge to this point. So often they have some sort of assumption to make sure that it's really a saddle point and not like an inflection point or something like that. I'll give the caveat here that everything I say about non-convex optimization is going to be ultimately unsatisfying. Because... What's that? You get the bad news fast. That's a good way of putting it, yes. Yeah. Yeah, so this slide was saying you learn the bad news fast, and this slide was saying, well, some methods can actually, it's not that bad of news. You can get unstuck from certain situations.
I think it's also the case of Frank-Wolf's algorithm method. You
Yeah.
also escape from this noise, right? Paper on non-convex optimization, and there is a
I guess that would make sense. So if you're doing Frank-Wolf with a line search, then you might be able to skip over like a non-convex region or something like that. I haven't seen that paper.
The idea was to minimize the L0.
Oh, okay.
So basically, the author he replaced the L0 by approximation, which is non-convex.
Yeah. Oh, okay. That sounds like Mark to Boole, but I'm not sure about that. It sounds like Mark to Boole.
No.
Okay. because I know he did some Frank Wolf for L0 stuff. Okay. There is a little bit of good news in that there are some non-convex problems we can actually solve. So the classic one is PCA. PCA is definitely a non-convex problem, but when you take your undergrad linear algebra course, they'll tell you that PCA is no problem. It's just an eigenvalue problem. So one way to write it is like this, where we have sort of a convex objective and we have non-convex constraints, but it's actually okay. And recently there's even been like SAG and SVRG variants of this, where they solve the non-convex PCA problem but much faster, or for bigger data sets. There's also work looking at reparametrizing SDPs. So if I have this problem of minimizing f of x, subject to x being positive definite, but having a rank constraint, so rank constraint is non-convex, they looked at reformulating with this VV transpose representation, which makes it non-convex, but they showed that this actually doesn't introduce spurious local minima. So you can still introduce critical points, but the local minima are actually going to be minimizers of the original function. So that's kind of neat, but I guess it's also not satisfying because the original problem was, other than the rank, was convex. So that's kind of neat. And there's been some generalizations of this recently. So there was a paper last year that looked at problems of this form, and they showed that if you use some sort of random initialization, you can get the global optimum. And this includes a few problems that people care about. And there's also been some work on trying to solve these in a statistical sense. So there's been work on using UV transpose representations of matrix to solve dictionary learning and phase retrieval problems. And there's also something called spectral methods, which are based on using either SVD or tensor decomposition. And those can solve problems like training hidden Markov models. So that's a classic non-convex problem, and we now have methods that are consistent, in that if you give them enough data, these methods will actually give you the right model, which is kind of neat. So this is, I think, the only slide that has any good news in the non-convex section. How do they know? Let me think about that. Okay, so this one, they're not solving the problem of global optimality. They have a different definition of optimality. They're saying that if my data satisfies certain assumptions, I can find a matrix that is optimal in a statistical sense. This one, again, is the same thing. They're not actually solving the optimization problem, but they're giving a model you can query that has the optimal behavior without necessarily solving the problem. So this is very much a reparametrization trick, where you're solving a different problem that is in some sense optimal, asymptotically. There's a consistency argument there, so you need n to go to infinity for this to solve the problem. So it's a little bit magical. And it's stuff that I don't know well. This is what we're covering in my reading group this summer, so I'll be able to say more meaningful things at the end of the summer. Okay, so there's also things like convex relaxations, where you approximate non-convex with convex. So in the case of deep learning or neural networks, there's been a few of these that have been looked at. So those tend to either solve a restricted problem or a bad approximation in the case of neural networks. For other applications, there's actually very good convex relaxations, but I initially was presenting this for the deep learning people, so for those ones, the convex relaxations are awful. And the reason they're awful is because these models have a lot of symmetries. They have a lot of label switching, where if I take some set of the variables and another set of the variables and I rename them, then I actually get the same model. When you have symmetries like that, the convex relaxations tend not to work very well. And that's only one of the problems in that setting. You can also go to the convex dual. So sometimes strong duality holds for non-convex problems. Sometimes the dual has nicer properties. The dual is always convex. In the case of neural networks, when I first showed this slide, I asked, I don't even know how you compute the dual of these models. So I don't know if anyone's looking into that or what the difficulty of that would be. And then there's also exact convex reformulations of non-convex problems. So you can look at something like the Lasserre hierarchy, where you can exactly write a non-convex problem as a convex problem, but with the caveat that the convex problem might be so huge that you don't really have any hope of solving it anyways. Okay, so I think that's all I want to, okay, I have one slide on the sort of the global problem. So we said already that grid search or random search is optimal, but you can actually beat it once you start making assumptions about the function. So there was a paper in 2011 looking at Bayesian optimization, which I can't remember the name of in the OR community. I think it's surrogate-based optimization or something like that. So this is actually, the result is kind of interesting. So if you have a low level of smoothness, the result actually implies that this is worse than grid search. So if you have a function that's not very smooth, you actually get worse than grid search. But if you have a high level of smoothness and you have a bunch of other assumptions, like your function comes from some nice Hilbert space type of thing, then it improves the error from O of 1 over epsilon to the D to 1 over epsilon to the D over V, where V is some measure of the smoothness. So you can actually solve higher dimensional problems if you have sort of this algorithm which assumes your function is sort of nice and smooth in some way. Yeah, I think C infinity is like the ideal case, and then like once, but it's not exactly just continuous. It's a little bit stronger than that. But that's the basic idea. Is if the function is higher order smooth, then you have a better you need less evaluations of it to find the optimum. Well, this is a global method, so it can, and it's just actually it's just optimizing in a box too. So there's not really a notion of step size, but you can make smarter steps maybe would be the way to say it. Okay, if we're talking about regret, that regret thing I defined earlier, you can define regret for an optimization problem instead of for these generic sequences. There was a paper showing that, yeah, regret goes up a lot, but if you start making assumptions about the function, you can show that the regret is better for these algorithms. So we're actually talking about derivative-free methods for general non-convex problems and saying that once you start making assumptions about them, you can solve them faster than grid search. It's something that's obviously true because for convex problems, we're always talking about making extra assumptions to make them easier, and there's no reason we can't do the same for non-convex problems. And that will probably be an important thing. Now, if you look around, if you do a lot of Googling about non-convex stuff, I spent like many days trying to find every sort of non-convex convergence rate result possible, and I believe that these two papers say something about convergence rates. I actually know Arnaud Doucet very well, so I need to ask him the next time. So particle filtering is also called sequential Monte Carlo or sequential importance sampling. It's actually very similar to genetic algorithms, and you can show that under certain conditions they improve the rate. There was this paper here which I completely did not understand, but it seems to indicate that simulated annealing is faster under some very complicated assumption. And then there's this paper which is much more recent and very easy to understand, where they define the class of sigma nice functions, and they show that something that's kind of like simulated annealing also works better for that class of functions. Okay, so all right, so I'll end there by saying, okay, so parallel and distributed methods, those are just going to be required in the future. And now you have some new things you need to think about, like asynchronous, low communication, fault tolerance. And we're starting to be able to understand non-convex problems a little bit, but I think there's a lot of work to do here. And if you're a PhD student looking for a topic, there's definitely ample things you can think about. Okay, so I do have some more material if people are interested, but this was kind of like the end of the prepared material. So finally, I just want to say thank you for inviting me to come here. Thank you for coming out to the lectures. This is my first time to Brazil. Even though it rained for the second half of my visit, I came here early and spent some time on the beach and hiked Mount Tijuca and things like that. So it's been amazing. So thank you so much for having me here. And I hope you actually learned something, so it was actually beneficial to people here too. So I hope that went both ways. Okay, so that's all of the material I've prepared.